So I wanted to spend a little bit more time talking about some of the code in this Jupyter notebook on computing the fundamental transition of CO using perturbation theory, which we started in lab. And although there's not a ton of new code to write to complete this notebook, there is a few things going on that are a little bit complicated. So I just wanted to spend some additional time talking about it. So, to recap, there's the fundamental idea here is we have this Hamiltonian for the vibrational motion of a diatomic molecule, and we can think about this Hamiltonian under a few different levels of approximation. So we could say we're going to have this Morse oscillator model for the Hamiltonian, and so we've got the kinetic energy operator plus this Morse potential, where this Morse potential is defined through this expression here. And in this particular case, I've given the parameters for the Morse potential for the CO molecule. So we've got this dissociation energy, which is about 11.2 electron volts. The equilibrium bond length is about 1.1 angstroms. I have this beta parameter, which kind of gives the curvature of the potential, has 2.5 inverse angstroms. And the reduced mass, which shows up in the kinetic energy operator, is 6.860 atomic mass units. Okay. Now, so the nice thing about the Morse oscillator is it has an analytic solution. So we can actually write down the energy eigenvalues of that Morse oscillator through this expression here, right? So I have this term which looks like the harmonic oscillator term h bar omega times n plus 1/2, where n is the quantum number. And then I have this additional anharmonicity term, chi sub e, which is going basically as the quantum number squared. And the omega term can be expressed through the Morse oscillator parameters, in particular dissociation energy times beta squared over mu, that whole thing times 2 in square root. And then the anharmonicity is h bar omega over 4 times the dissociation energy. Okay, so we have that Morse oscillator model, and it's a nice sort of form for the potential that gives you an analytic solution. But we remarked that oftentimes what we're actually going to do is sort of sample the potential through some sort of quantum chemistry technique. And there it can be actually really helpful to think about defining some kind of Taylor expansion for our potential, where I have these sort of successive orders of the displacement from equilibrium. And so I can have, for example, the quadratic order in this Taylor expansion, which is exactly equal to the harmonic oscillator potential. So I have like 1/2 k times the displacement from equilibrium squared, and then the k is going to be given by the second derivative of the potential evaluated at equilibrium. I can have a cubic term where I have the third derivative of the potential evaluated at equilibrium. And then I can have a quartic term, which is going to come from the fourth derivative, and so on. And if I think about approximating the Morse model in this Taylor expansion, I can actually write down these different harmonic, cubic, and quadratic coefficients analytically. But I may not be able to do that because, again, I may actually be sampling some quantum chemistry potential, and then I'm going to actually have to approximate these derivatives using something like finite difference methods. And this is an expression, for example, for the finite difference approximation for the second derivative of the potential, which we can take. Okay, so now one of the main things that we want to illustrate in this notebook is the use of perturbation theory to approximate the solutions to the Schrodinger equation when I can't find them exactly. And so again, this is now one of the reasons why we would want to invoke this Taylor expansion for our model for the potential, because then what I can think about doing is setting up a really nice kind of problem for perturbation theory, because what that allows me to do is sort of say that the total Hamiltonian is going to be equal to the kinetic energy plus this harmonic potential plus some perturbation, right? And so I can actually know the solution to this piece right here. So I'll call that my 0th order Hamiltonian. And then I just have to find out ways to correct my solutions subject to this perturbation, where the perturbation could be, for example, just the cubic term, or it could be the cubic plus the quartic term. And in fact, we're gonna look at both of these cases as time goes on through this notebook. Okay, and then that being said, what I can do is I can actually set up an expression for my energy, where I have my energy up to 2nd order is given by the 0th order energy plus the 1st order correction plus the 2nd order correction. And the 0th order energy, if I define my 0th order Hamiltonian to be the harmonic oscillator Hamiltonian, then the 0th order energy is just going to be the harmonic oscillator energy, which is going to be going like h bar omega times n plus 1/2. And then the 1st order correction, right, I just need my 0th order states, which are the harmonic oscillator states given here, taking brackets with the perturbation. And then the 2nd order correction to the energy is a little bit more complicated. I am going to have these brackets with the perturbation, but in this case, if I'm trying to find the correction to state n, where maybe n is the ground state, so n equals 0, I'm actually going to take those psi n states as the ket, act on those with this perturbation, and then project onto a bra, which is a different state, and divide that by this denominator, which is the difference between the 0th order state I'm trying to find and the 0th order state for state k. And I'm going to sum up over some number of k, where k can take on different values of the quantum number different than the quantum number for the state I'm trying to find. So again, if I'm trying to correct for the ground state, n will be equal to 0, and I'll just sum up over values of k not equal to 0. Of course, I have to stop at some point. I can't just keep going to some infinite number of k. So perhaps I'll have something like 100 different values, and I'll sum up over 100 different kind of brackets right here. Okay. So this is sort of an outline of this approach. Okay, and here what we're going to do is we have this notebook. We have the Morse parameters defined in this first block. So I'm going to do all my import statements here. I have some special libraries here, in particular this Hermite polynomial library from SciPy. That's going to help me define the 0th order states. I'm going to do some numerical integration using the trapz function and numpy. That's going to help me actually compute these brackets here. Okay. So now I have these parameters set up, and the other thing I'm going to do is I'm going to actually convert all of these parameters into atomic units. And so I've got my dissociation energy, for example, and EV. I'm going to convert from EV to atomic units of energy, which are sometimes called the Hartree. I have the equilibrium bond length in angstroms. I'm going to convert that to atomic units, which is sometimes called Bohr radii. And then I have the reduced mass in atomic mass units, and I'm going to convert that to atomic units of mass. So here are some conversion factors for doing that. And this is a block where I'm going to convert all of those parameters into atomic units. Okay, so here I've got in atomic units my dissociation energy, dE underscore AU, my reduced mass in atomic units, mu underscore AU, my equilibrium bond length in atomic units, REQ underscore AU, the beta parameter in atomic units, beta underscore AU, and then H bar in atomic units, which is H bar underscore AU. And a nice thing about atomic units is that in atomic units, H bar is 1. Okay, so we already wrote this on together on Friday, but this is a function to evaluate the Morse potential. And this is going to give us kind of a reference potential that we're going to be building approximations to in the first part of this notebook. Okay, so it's going to take some arguments. I've got the bond length R, the dissociation dE, the beta parameter, the equilibrium bond length, and it's going to return the Morse potential. And importantly, right, you want to think about this function as being, pretty general and reusable. So you don't necessarily want to think that these values are being passed in any particular unit system, right? You just simply want to assume that they're in a consistent unit system, so that all you have to do is really evaluate the math. Okay, and so that's what we've done here, right? We've just basically applied the expression for the Morse potential right here. And then now what I'm going to do outside of this function, so you can see that this is all within the function because it's at this level of indentation, right? And then I'm going to unindent and be outside of the function, and I'm going to define an array of bond lengths between 0.2 atomic units and 2.5 times the equilibrium bond length. And there's going to be 20 of those bond lengths, and that will be all stored in this array called R. And then I'm going to pass R to my evaluate Morse function here and give it the dissociation energy in atomic units, the beta in atomic units, and the equilibrium bond length in atomic units. So every argument to this function has been put into atomic units, and so overall then the Morse potential itself will be in atomic units. And I'm just going to go ahead and add a plot statement so we can see the Morse potential. Okay, so I've got my Morse potential plotted. I have a little label here. I'll go ahead and add actually plot X label, potential, and atomic units, and plot Y. Oh, that's actually the Y label, sorry. And X label is going to be bond length. And let's see what we get. Okay. So the potential in atomic units is along the y-axis. The bond length in atomic units is along the x-axis. And this is what we get. So this is the Morse potential. This looks how it should look, okay? So everything seems good. Okay, now come down here. So these are lines that I have not yet completed. And what we're going to do is we're going to expand this Morse potential as a Taylor series, right? And so we have these nice analytic expressions for the quadratic, cubic, and quartic terms. And so what I'm going to do here is I'm just going to use these expressions, and I'm going to define these terms in atomic units, right? So in fact, I'm going to simply just find these lines here. They have these little comments, right, that point to the variable I'm supposed to assign, and then I'm going to delete the comment and assign the variable. So I can see right above my expression for K is 2 times the dissociation energy times beta squared. So I want to use that expression, and I just need to make sure that I'm using the versions of these variables that are in atomic units. So dE underscore AU is dissociation energy in atomic units, and beta underscore AU is beta in atomic units. Okay, and so there we go. I've got K, hopefully in atomic units. I'm going to do the same thing for G. So minus 6 times dissociation energy times beta, all in atomic units. And then H, it's going to be equal to 14 times dE underscore AU times beta underscore AU to the 4th power. Okay, so now here's what I'm also going to do. I basically want to take this expression here and try to numerically approximate K using the Morse potential. And so what I'm going to do then is I'm going to use the centered finite difference expression, where this is telling me that the second derivative of this potential evaluated at REQ can be given by the following expression. The potential evaluated at REQ plus a little bit forward minus 2 times the potential evaluated at REQ plus the potential evaluated at REQ minus a little. And that whole thing in the numerator is going to be divided by the little displacement, delta R, squared. Okay, so here I have actually already predefined the displacement, delta R, and I'm going to have that displacement defined as 0.001 times the value of the equilibrium bond length. Okay, so if the equilibrium bond length, which we can kind of guess from above, is about 2 and change atomic units, so then the displacement is going to be about 0.002 atomic units. Okay, so think about this for a second. I want to get the value of the potential at the forward displacement, so REQ plus delta R. And so how could I do that? So remember, I have a function that I just wrote. It's called evaluate Morse. And I give it the Morse parameters dE, beta, and REQ, and I give it a value or values of R. So what I'm going to do is I'm going to use evaluate Morse, and I'm going to insert as the first argument R underscore EQ underscore AU plus delta R, right? Because that's going to be the equilibrium bond length plus delta R, comma DE underscore AU, and then what are the other arguments I need? Beta and REQ AU. Okay, so that should be my value of the Morse potential displaced by a little bit, delta R. Okay, now I need it at equilibrium, so I'm going to delete this comment, use the same function, evaluate Morse, just evaluate it at REQ. And then finally I need it at the backward displacement. So I'll delete those comments. VB is equal to evaluate Morse REQ AU minus delta R DE underscore AU beta underscore AU REQ AU. Okay, so those are my 3 different values of the potential that I need for this numerator. And then now that gives me K num. The numeric approximation to K is going to be V, I'm going to put this in parentheses, V underscore F minus 2 times V EQ plus VB, and this whole thing over, in parentheses, delta R okay, so that should be my numerical approximation to K. And here, what I'm going to do is compare the numerical and analytical evaluation of K. I'm actually going to print both of them, the numeric first and then the analytical, and then I'm going to evaluate this assert statement. And if it passes, or sorry, I'm going to evaluate this close comparison, and if it passes, and then if it passes, it's going to say that these things agree to within plus or minus 10 to the minus 4 atomic units. Okay, so let's run this cell and see what happens. Okay, so great. Here's the numerical, 1.56107, and here's the analytical, 1.56106. So they do indeed agree to plus or minus 0.0001 atomic units. So that's pretty good. And I'm just going to show you what happens if I make the displacement a little bit coarser. okay? So actually I made it 100 times coarser. So the displacement is a lot larger. Now all of a sudden, there's quite a big disagreement, okay? So, so this 10 to the minus 3 displacement size is important for achieving this kind of precision, okay? All right, so now we have these different coefficients that define our Taylor expansion of the potential. And so let's go ahead and run this block and see the different contributions, okay? So I've got the Morse potential itself right here in purple, and I have the harmonic potential in red, okay? And so just looking at purple and red for a minute shows kind of the important difference between the harmonic potential and the Morse potential that we discussed in class. So the two are not so bad, near equilibrium, but as I start to stretch, the harmonic it goes up too rapidly compared to the anharmonic potential. And as I compress, it goes up too slowly, okay? The cubic, on the other hand, right? So the cubic looks pretty close, except for it starts to turn over and become negative as I displace, right? So that's that sort of cubic behavior kicking in. But the chordic potential can actually kind of correct me back up towards the anharmonic or the Morse potential a little bit better. And so you can see that actually I have pretty good agreement between the green curve, which is including up to the chordic term, for relatively large values of displacement, okay? But even if I go to large enough displacement, of course, the chordic still rises too rapidly compared to the full Morse potential. Okay. So now, the things that I need to do to complete this notebook are actually relatively small. One of the things that I need to do is actually fix or complete this function compute alpha. And then this alpha is defined as the square root of k times omega times h bar, okay? And so omega, you might remember, is equal to the square root of k over mu. So that's how we get the fundamental frequency in the harmonic approximation. So I'll say omega is equal to square root of k over mu. And then now alpha itself is going to be equal to square root of k times omega divided by h bar. And then I'm just going to return alpha. Actually, it's already returned. Okay. So that is a helper function which is going to be used in order to find our zeroth order states, which I'll just remind you, the form of the zeroth order states comes from the notes up here. So the zeroth order states are kind of this complicated normalization function times this alpha over pi to the 1/4 power times these Hermite polynomials of order n, which take as arguments square root of alpha times r times these Gaussian functions, which again have alpha in them. So you can see basically every term has alpha in it. The normalization has alpha in it. The Hermite polynomial has a square root of alpha as its argument. The Gaussian has minus alpha as its argument. Okay, so we definitely need alpha for those functions. All right. So what else do we need? The normalization is already defined. And then these psi helper functions are also already defined. So this is basically going to put everything together for the zeroth order states, the harmonic oscillator states for quantum state n. So it's going to take as arguments the quantum number n, the parameter alpha, the value or values of r that you want to evaluate the function at, and the equilibrium bond length. Okay, so you'll pass those all as arguments. We're going to get the Hermite polynomial at order n as this sort of object here. And this object is actually going to be callable. So this is sort of a funny little library in SciPy where you're going to return sort of a callable function, which is going to be defined as the Hermite polynomial of some order. So this right-hand side here is going to sort of return for you another function of order n, and that function will be the Hermite polynomial. So HR now is going to be something, it's not actually just a normal variable, it's actually going to be like a callable function. And then down in this line here, I'm going to define a NumPy array, which is going to be given by this number here, which will be the normalization constant. The normalization constant was computed using this helper function, which was already written for you, multiplied by that callable Hermite polynomial, which is going to be taking as an argument square root of alpha times r minus REQ. And then finally, I'm going to have this Gaussian function, e to the minus 1/2 alpha times r minus REQ squared. Okay, so as long as R is a NumPy array, this whole thing is going to be a NumPy array and will return a NumPy array. All right. So the last thing that I'll kind of walk through before we run this line down below to test out the eigenfunctions is this compute potential matrix elements. Okay, and so this is one more helper function which we're going to use along with our perturbation theory, because basically what we need to do in order to compute the corrections to the harmonic potential is we need to take these zeroth order states, right, these harmonic oscillator states in the bra and the ket, and then sandwich them with these potential terms. And so we're going to have to take these sort of brackets of this form, where I'm going to have some harmonic oscillator state on the bra multiplied by some potential term multiplied by another harmonic oscillator state on the ket. So this function is going to compute those matrix elements, and you're going to give it a few different arguments. Okay, you're going to give it the quantum numbers for the bra, which is going to be n, and the quantum number for the ket, which is going to be m. You also need to give it alpha and r and REQ. These are the things necessary to evaluate the functions on the bra and the ket, these first 5 arguments. And then V underscore P is the perturbing potential. That's basically the operator that you're going to use in the bracket. Right, so if you come down here, you can see I'm going to compute the bra state here using the psi function that we just looked at above. I'm going to calculate the ket state here, again using the psi function, and the only difference is the quantum number, right? The bra quantum number is n, and the ket quantum number is m. And then I'm just going to define an integrand. It's going to be defined as the complex conjugate of psi n multiplied by the perturbing potential multiplied by psi sub m. And then I'm going to integrate that integrand on my real space grid R using the NumPy trapz function, and I'm going to return it. Okay, so let's go ahead and run all of those cells, and now we can test out a couple of features. So number one, we're gonna, oops, that I get an assertion error. That doesn't look right. Probably this expression for alpha is wrong. That looks even worse. U omega over h bar. Okay. That looks a little better. Something really crummy about my grid, but that's okay. What do we get? What is the value of this integral? 1.4. So anyway, that's interesting. So this is the ground state, and it does not look very good, but I think that's probably just because my grid of R values is really, really coarse. So I'm going to try to fix that really quickly. Let's do the following. Let's maybe change this to 100 points. So now that potential looks a lot more smooth. Ah, perfect. Now this is looking a lot better. Okay. And let me just, now that I've kind of troubleshooted this block, let me just tell you what I did. So here I computed alpha, right, using k and mu and h bar. Then I computed size 0, the ground state, 0th order ket, using that value of alpha on this real space grid R. And then what I did is I took the integral of size 0 squared along R. And if this is a normalized function, then this integral should be equal to 1. And that's what I find. It's very, very close to 1. So I have a properly normalized psi 0. Let's go ahead and just look at psi 1 as well. Okay, here's psi 1. That also looks like the first excited state of the harmonic oscillator. It's starting to look a little spiky. So this might indicate that I need some more points. If you do find your functions are looking spiky, you can just increase the number of points in your grid, and that should help things. So let's go ahead and go up to 500. That's not going to hurt anything. Okay, great. So now things are looking even more smooth because I have added even more points. And I don't know, let's go to psi 4. Okay, so you can see I can get all of these different eigenfunctions out of this little helper function that I wrote. And there we go. And the last piece is going to be actually computing the corrections, but I will save that for when we meet in class this week. I hope this was helpful. See you all soon.